Lecture problem 2. A student exerts a horizontal force of 10.0 newtons with his hand and pushes a 5.0 kilogram box initially at rest a distance of 3.0 meters across a frictionless floor. Calculate the magnitude of the work done by the student and the speed of the box at the 3.0 meters mark. This is obviously an energy-related question, and a free body diagram can be very useful. The box is sitting on a horizontal frictionless floor, and it's under three forces. The weight mg is acting vertically downward. The normal force is acting straight up. And finally, the force of the student, which is acting towards the right. That's the force F. And as a result, the box is going to be displaced a distance d along the horizontal. The first question is related to the work done by the student. Since the force that is exerted by the student's hand on the box is a constant force and it is equal to 10 newtons, therefore the work done by a constant force can be evaluated using the following expression, Fd cosine theta, where the angle theta is the one that is made between the force of the student and the displacement. Clearly, the force of the student is pointing towards the right, so is the displacement. Therefore, the angle made between the force and the displacement in this case is equal to 0. Substituting the force and the displacement by their values, the force is equal to 10 newtons. The displacement is equal to 3.0 meters. The angle, as I stated, is equal to 0, and the cosine of 0 is equal to 1. Therefore, the work done by the student force is equal to 30 joules. The second part of this question is about the speed of the box after it travels 3 meters. Notice that the speed can be found within the kinetic energy. Therefore, the best tool to use here to solve for the speed at the 3 meters mark is the work energy theorem, where the work done by the net force equals the change in kinetic energy. Notice that there are three forces, therefore there is a work done by the normal force, a work done by the weight mg, and a work done by the force F. We need to evaluate each one of them. So the work done by the force F of the student plus the work done by the normal force and the work done by the mg, all added algebraically in the form of scalars, equal the kinetic final minus the kinetic initial. Notice that the work done by the normal force is going to equal 0 for the simple reason that the normal force is making a 90-degree angle with the displacement. Anytime a force makes an angle of 90 degrees with the displacement, that force always does 0 work. Notice in this case also, the mg is making a 90-degree angle with the displacement. The weight mg is acting straight down, and the displacement is lined up along the horizontal, pointing towards the right. So the angle is equal to 90 degrees. In this case, the mg is also doing 0 work. Since the initial speed of the box is equal to 0, therefore the initial kinetic energy has to equal 0. Remember that the kinetic energy equals 1/2 mv squared. So this quantity is also equal to 0. As a result, this equation is reduced to the following. The work done by the student force equals the final kinetic energy, which is 1/2 mv final squared. Substituting the known quantities, the work done by the student force, we have solved for that one early on, which equals to 30 joules, equals 1/2. The mass of the box is equal to 5.0 kilograms, times the final speed squared. Solving for the final speed Vf, we obtain 3.5 meters per second.